Hello and welcome to tutorial session 11. So today's session, problem solving session, we are going to cover some sample problems from waveguides, parallel plate waveguides and rectangular waveguides. So as we see the last week's discussion, that is week 12, discussion is on cavity resonators and their applications. Uh, so if you see, cavity resonator is an extension of a rectangular waveguide, and you have seen that video. You might have gone through the video lectures, and you could have got the idea of what is a cavity resonator, and some practical real life examples have been discussed in the video lectures. So uh, let's move on to solving some sample questions. So for today's session, I would like to cover a few questions from waveguides. Especially this week, I'm trying to solve some gate questions from the portion waveguides. So every question is taken from one or the other gate question paper. So let's move on to our discussion, starting with some of the 1 mark questions in GATE. So you can see the corresponding GATE paper is written next to the question. So based on our understanding of waveguides, I believe we can go through this and we can try to see our understanding of the content based on waveguides. So coming to the first question, the interior of a 20 by 3 into 20 by 4 centimeters. So this is A cross B. So the dimensions of the rectangular waveguide. It is completely filled with the dielectric of epsilon r equal to 4. Waves of free space wavelength shorter than some wavelength, okay, can be propagated in the TE11 mode. Okay, so coming to propagation in a particular mode inside a rectangular waveguide, what do we learn is, for a particular mode there will be a cutoff frequency, and f greater than fc, that is all the frequencies greater than fc propagates in the waveguide or survive in the waveguide. Or in terms of wavelength, we can say lambda less than lambda c propagate. So this is what. So waves of wavelength shorter than this cutoff wavelength will be propagated in the TE11 mode. So the mode which we are concerned here is the TE11 mode. So how to calculate the FC for that particular mode? We have the fundamental equation. Because it is a dielectric filled waveguide, I have to say V by 2 into square root of m by a the whole square plus n by b the whole square. Now let's see each of these parameters. V is c by root epsilon r. So 3 into 10 power 8 divided by root 4. So this comes out to be 3 by 2, that is 1.5 into 10 power 8 meter per second. Then m and n, that is the mode number, m is equal to n is equal to 1. So, and a and b values are known to us here, 20 by 3 and 20 by 4. So coming to substituting here to get the cutoff frequency, fc is equal to 1.5 into 10 power 8 by 2 into square root of m and n values are 1 and a value is 20 by 3. So 20 by 3 whole square plus 20 by 4 whole square. Okay. So once you simplify this, you get a cutoff frequency. Here, this, if you calculate, you get it as 1.875 into 10 power 9 gigahertz. 10 power 9 hertz, sorry, or 1.875 gigahertz. Okay. Now, you know the cutoff frequency. So, what is cutoff wavelength? Lambda c. Lambda c is V by Fc. So, V is 1.5 into 10 power 8 by 1.875 into 10 power 9. So, final answer would be 8 centimeters. Okay. So, this is the cutoff wavelength. So, any wavelength less than that cutoff wavelength will be propagating in the TE11 mode. Okay. So, any wavelength less than 8 centimeter here, okay, will be propagating in this particular rectangular waveguide, which is filled with the dielectric, and we are concerned with the particular mode TE11. Hope this is clear. Now moving on to the next question. Uh, so next question is a rectangular air-filled waveguide. So it's a question on air-filled waveguide. Has a cross section of 4 into 10 centimeter. Minimum frequency which can propagate in the waveguide is. So the question is on the minimum frequency which can propagate, and we have 4 options also. So let's see. First, let us note down the dimensions of the waveguide. So if you see 4 into 10, so the longer dimension is A and smaller dimension is B. So here A is 10 centimeter, B is 4 centimeter. Okay. Then this minimum frequency which can propagate. So that will be your cutoff frequency. Here it's an air-filled waveguide. So the cutoff frequency Fc will be C by 2 into square root of m by a the whole square plus n by b the whole square. Okay. Now the least value of m and n. Okay. Say if this is TE mode. Okay. For TE mode m n. Okay. So the least value is 1 0. Okay. M1 and M0. So TE10 mode is known as the dominant mode in case of a rectangular waveguide. TE10 mode is called as the dominant dominant mode, for which the cutoff frequency is the smallest. Okay, so let's calculate that for TE10 mode. So substituting m as 1, this comes out to be 1 by a, m as 0. So C by 2a. 3 into 10 power 8 divided by 2 into 10 centimeter. So maybe we can make this also as centimeters. 10 power 2. So what we get is 1.5 gigahertz. Okay, so we calculated the cutoff frequency, and so that is going to be the minimum frequency which can propagate. So this is option A, 1.5 gigahertz. Now coming to the next question, that is the third question. Indicate which one of the following modes do not exist in a rectangular resonant cavity. Okay, so this question is about a rectangular resonant cavity. Okay, so in this particular cavity, which mode does not exist? That is the question. Okay, so in case of a cavity resonator, to be specific, a rectangular cavity resonator. Okay, case of a rectangular cavity resonator, we can say, so this is A and this is B, and in case of cavity we will specify this particular length also, that is D. Okay, so all these three parameters A, B and D. Now mode number in case of a cavity resonator will be represented in terms of M, N, P. Okay, in case of rectangular waveguide we had only M and N. In case of a cavity resonator we have a third mode number, that is M, N and P. So this represents X, Y and Z directions. Okay, now in case of TE mode and TM mode, so there are two options. It could be a TE mode or it could be a TM mode. Now TE mode and TM mode, which one of these in the options, which one among these in the options does not exist? That is the question. Okay, in case of a rectangular resonator, TE110 does not exist because the lowest value of the last subscript, that is MNP, last subscript is 0. Okay, for a TE mode to exist, that last number should be 1. Okay, so this is the mode TE110 is the mode which does not exist in case of a rectangular cavity resonator. So if you to make it more clear, if you look at the equations for TE and TM modes, in case of TE mode, in case of TE mode, say TEMNP. Okay, what is HZ? HZ is H naught Z cos of M pi x by A cos of N pi y by B sine of P pi Z by D. Okay, so in this case, in this particular case, suppose if P is 0, okay, if P is 0, sine 0 becomes 0, in this in which this field value Hz value does not exist. Okay, so the P has to be 1. Okay, at any cost, for the TE mode to exist, P has to be 1. Okay, That is why we say TE110 will not exist in the rectangular cavity resonator. Okay. Similarly, to check for TM mode, so TM is TMMNP. So let's write the equation for EZ. EZ equation is E naught Z sine of M pi x by A sine of N pi y by B cos of P pi Z by D. Okay. In this particular case, if you see, M and N should not be 0. Okay. M, N has to be 1. Okay. At any cost, M and N should be 1. It can never be 0. Okay. So, in both the options, M and N are 1. So, these two will exist. But in this case, this will also exist. But this one, last digit is 0. Then M and P is equal to 0 here. So, P is equal to 0. In this equation, if you substitute, this HZ will go to 0. Okay. That's why for TE mode, P can never be 0. P not equal to 0 for a TE mode to exist. Hope this question is clear. Okay. So next question is on phase velocity. We had a discussion on phase velocity in the previous week. So this is a very simple question based on that. Let's read it. The phase velocity of the wave propagating in a hollow metal waveguide is greater than velocity of light in free space. Okay, so Vp, let us indicate Vp. So this statement indicates that Vp is greater than C. And second statement, Vp is less than C, less than the velocity of light in free space. And the third statement, Vp is equal to C. Okay, and the last statement, Vp is equal to Vg. Okay, so among this is very easy and simple understanding. First option is correct. Always Vp will be greater than C. To just to refresh that concept, if you remember, Vp is equal to C by square root of 1 minus Fc by F the whole square. Okay, so where Fc is the cutoff frequency of that particular mode, F is the operating frequency, C is the velocity of light in free space. So from this equation, it's very clear that Vp will be always greater than C. Okay, Vp will never be equal to C, or Vp will never be equal to will be never be less than C. Okay, and Vg and Vp are different. All of you know that Vg is C into root of 1 minus Fc by F the whole square. That is group velocity. Coming to the next question. This again very basic question. Dominant mode in a rectangular waveguide is TE10 because this mode has option A no attenuation, option B no cutoff, no magnetic field component. The last option is the highest cutoff wavelength. Okay, so it's a very simple concept. Dominant mode is the one which will have smallest cutoff frequency, or we can say highest cutoff wavelength. Okay, highest cutoff wavelength lambda. Okay, so the last option is correct. Sixth question, it's again a repeated question. We can just go through it. Phase velocity for the TE10 mode in air-filled rectangular waveguide is always greater than c. Coming to seventh question, phase velocity of an EM wave propagating in a hollow metallic rectangular waveguide in TE10 mode. A question is little modified, but still the answer remains same. Phase velocity is greater than velocity of light in free space. Okay, so this has been repeatedly being asked. So the concept Vp greater than C is applicable in any mode situation. So Vp greater than C, phase velocity is always greater than the velocity of light in free space. Now coming to eighth question, refractive index of glass is 1.5. Find the wavelength of a beam of light with a frequency of 10 power 14 Hz in glass. Assume velocity of light is 3 into 10 power 8 meter per second in vacuum. Okay, so the question is, you need to find the wavelength. Okay, in case of this question, you need to find the wavelength. You are given with the refractive index of the glass, and you are also given with the incident wave or the beam of light, the frequency of that beam of light. So let me write the frequency of that light beam, 10 power 14 Hertz. Okay, then velocity of light, that is c, 3 into 10 power 8 meter per second. Okay, now how to find out the wavelength? So when we say refractive index n, this is c by v, where c is the velocity of light in free space and v is the velocity of light in the medium. So this refractive index is a ratio of c to v. Now from this we can find v. V is equal to c by n. Here you have 3 into 10 power 8 divided by n value is 1.5. So this will be 2 into 10 power 8 meter per second. You see? So in vacuum, the speed is 3 into 10 power 8 meter per second. Whereas if the light beam passed through a glass of refractive index 1.5, then the speed is 2 into 10 power 8 meter per second. Okay. Now the question is, what is the wavelength? The fundamental relation is v, velocity is equal to f lambda. So lambda is v by f. 2 into 10 power 8 divided by, what is f here? 10 power 14. So we get it as 2 into 10 power minus 6. So meters. So we can write 2 micrometers. So the option is C. So this will be the wavelength of the light which pass through that particular glass. Coming to the next question, which of the following statements is true regarding the fundamental mode of the metallic waveguides shown? So if you see, three waveguides are shown below. One is the coaxial, that is indicated with the letter P. So this is a coaxial cable in which you have a center conductor and an outer conductor. And the second is a cylindrical waveguide, and third is a rectangular waveguide, P, Q and R. In this, uh, so this, if you see the statements, only P has no cutoff frequency, only Q has no cutoff frequency, only R has no cutoff frequency. And the last option is all three have cutoff frequencies. So if you see, a rectangular waveguide and a cylindrical waveguide will have cutoff frequency. But in a coaxial waveguide, there is no cutoff frequency. So the answer is option A. Only P has no cutoff frequency. Coaxial, uh, it, so this cylindrical and rectangular waveguides, they are single conducting structures. So in this kind of structures, there will be cutoff frequency. And in these two, the TEM mode of propagation does not exist, or it is not possible. Whereas in case of a coaxial cable, TEM mode of propagation exists. In that case, there will be no cutoff frequency. So in two conductor systems like coaxial cable, TEM mode is possible and there won't be any cutoff frequency. Going to the next question. The modes in a rectangular waveguide are denoted by TEMN or TMMN, where M and N are the eigennumbers along the larger and smaller dimensions of the waveguide respectively. Which one of the following statements is true? Okay, so this is about the TE and TM modes in a rectangular waveguide. So let's read the statements. TM10 mode does not exist. Second option, TE10 mode does not exist. TM10 and TE10 mode both exist and have same cutoff frequency. TM10 and TM01 both exist and have same cutoff frequency. Okay. To answer this question, so this second statement is very evident. TE10 mode does not exist. This is not a true statement. Okay. There is TE10 mode that exists and that we call it as a dominant mode. That is very clearly, so this is not the answer. Now coming to the other statements here, to make it more clear, if you can refer to the electric field equations and magnetic field equations, it will be clear which mode exists. So based on the value of M and N, and substituting in the equation for electric field and magnetic field, then you will be able to understand which mode will propagate, which mode exists in a particular waveguide. So if M or N, say M equal to 0 or N equal to 0, in case of a TM mode, okay, in case of TM mode, M0 or N0 or both 0 is not possible. Okay, so we know that TM cannot exist. TM10, TM01, those kind of modes does not exist. So the answer is option A, that is TM10 mode does not exist. Why? Because here N is becoming 0. N can never be 0. So if N is 0, then that mode field does not exist. In case of TM, HZ should exist. In case of in case of TM, EZ should exist. Okay, in case of TM, HZ goes to 0, but EZ will exist. So if EZ goes to 0 when N is 0 or M is 0, then that mode does not exist. So that is the correct statement. These two statements are wrong. Now the 11th question. Consider an air-filled waveguide with a cross-section of 5 into 3 centimeters. For this waveguide, the cutoff frequency of TE21 mode is. So TE21 mode. So A is 5 centimeter and B is 3 centimeter and M is 2, N is 1. Okay, that is MN21, TE21 mode. So in this case, FC, the cutoff frequency FC is, so this is air filled, so we can write C by 2 into root of M by A the whole square plus N by B the whole square. So if you substitute 3 into 10 power 8 by 2 into square root of 2 by 0.05 the whole square plus 1 by 0.03 the whole square. Okay, so this is the cutoff frequency. So once you solve it, you will get the answer as 7.8 gigahertz. Okay, so that will be the cutoff frequency. Okay, coming to the next question. So far we have discussed some 1 mark questions in GATE papers. So now we'll move on to a little bit uh, harder questions, which are like 2 mark questions. So to understand the first question here, which one of the following does represent the electric field lines for TE02 mode? So let us write down the mode. This is very important. TE02 mode. That means M is 0, N is 2. Okay. M is along. So basically, if you see, M is along X direction and N is along Y direction. So this is along X and this is along Y direction. TE02 mode in the cross section of a hollow rectangular metallic vehicle. So if you see the options here, you can see the first option. Uh, there is field. There is a field which is having variation along the x direction, and if you see uh, the second option, this is along the, so the field is pointing towards x direction. So in option A, field is pointing towards y direction, and in option B, field is pointing along the x direction. Okay, coming to the option C, here you have two half waves. So when you say two half waves, so this is one half, this is the second half. Okay, so in this it is pointing along plus y, and in this first half it is pointing along plus y, and in the second half it's pointing along minus y. Okay, so if you see, the variation is along x direction. Okay, so there are two halves. Okay, first half, second half. So this m or n represents the number of half wave variations along x and y respectively. So here if you see, along x direction there are two half wave variations.
So here in this case n is equal to 2. Okay. Similarly, going to the last option, what is happening? The half, so this is one half, okay, and this is the second half. So here n is equal to 2. That means the variation, two half waves are along which direction? Y direction. So there are two half wave variations along the Y. So we can say, and there is no variation along the X. Okay, along X there is no variation. So if there is no variation, M will be 0. Okay, here along Y there is no variation, so N is 0. So here we want to find out M0 and N2. So the option is option D. Right option is last. So the similar way we can say here along Y, in the first option along Y there is no variation, and in along X, that is M is equal to 1, N is equal to 0. And in the option B, along X there is no variation, so M is 0, and along Y there is 1 half. Okay, when there are two halves, one half will be in this direction and the other half will be in the other direction. Moving on to the next question. Rectangular waveguide having TE10 mode as dominant mode. So let's say TE10 is the dominant mode, and it is having a cutoff frequency of 18. Okay, sorry. So make it more clear. Uh, is having a cutoff frequency of 18 gigahertz for the TE30 mode. So cutoff frequency for TE30 mode is 18 gigahertz. Okay, so TE30 cutoff frequency. FC is equal to C by 2 into square root of m by a the whole square plus n by b the whole square. N goes to 0 here and m goes to 3. Okay, so how it will be? C by 2 into 3 by a. Outside the square root it will be into 3 by a. Okay, so this FC is going to be 18 gigahertz. Now if that is the case, then inner broad wall dimension of the rectangular waveguide. That is A is the question. So it is very easy to find A, that is 18 into 10 power 9. So A is 3 into 10 power 8 into 3 divided by 2 into 18 into 10 power 9. So 1 by 4. One by 40. So that will be in meters. In centimeter is just 100 by 40. So it will be 5 by 2 centimeters. So the right option is C. Going to the next question. An air-filled rectangular waveguide has inner dimensions 3 into 2 centimeters. So this is question number 9. A is 3 centimeter and B is 2 centimeter. The wave impedance for TE20 mode of propagation in the waveguide at a frequency of F is operating frequency 30 gigahertz, and the wave impedance eta TE20, that is that is what you have to calculate, eta TE, and for 20 mode. Okay, so first what we have to do is, first we have to find the FC for this TE20 mode. So FC is equal to C by 2 into root of M by A is 2 by A the whole square. N is 0, so the next term does not exist. So finally what we get is 2 by A will come out, 2 gets cancelled, and finally it is C by A. So that is FC. So 3 into 10 power 10 divided by 3 centimeters. So this is going to be 10 gigahertz. Okay, that is your cutoff frequency for the TE20 mode. Now how do we find eta TE for that mode? Eta naught divided by square root of 1 minus FC by F the whole square, where F is the operating frequency 30 gigahertz, FC is the cutoff frequency 10 gigahertz. So if you substitute FC and F and eta naught value, we know that it is 377 ohms. So if you substitute all these, you will get the answer as 400 ohms. If you calculate, you will get 400. So the option is option C.
coming to next question, so which is from our GATE 2007 paper. You see, the electric field in a rectangular waveguide of inner dimensions A and B, or A cross B, is given by. So this is the expression for the electric field. Okay, if you notice, the electric field is in which direction? Y direction, and the components, if you see, so this is the whole constant term, and if you see that second term, it is sine of, and the other term is sine of again. So this is sine of omega t minus beta z, and this is of the form. So if you notice, this is of the form sine of m pi x by a in case of a rectangular waveguide. So by comparing, we can easily get m is 2. Okay. Now what is the question? Let us come to that. H naught is a constant. A and B are dimensions along x and y. And mode of propagation in the waveguide. So the question is mode of propagation. Okay. So if you see, m is 2. That is clear. And there is no function of the form n pi y by b. Okay. So it's clear that n is 0. Okay, so what will be the mode of propagation? Mode number will be 20. Okay, mode number will be 20. Now the question whether it is t or tm. Okay, so the wave is traveling in which direction? So if you see, sine of omega t minus beta z, so the wave travels along plus z direction. Okay, so the wave is traveling along plus z direction, and it has an electric field in the y direction, which is a function of only x. Okay, and there is no component along the direction of wave propagation, which means Ez is 0. For Ez is equal to 0, then we call that mode as what? TE mode. So now, joining all these dots, it's clear that it is TE20 mode. So the answer is option A, TE20 mode. Okay. Coming to the next question, a rectangular waveguide of internal dimensions A 4 cm and B 3 cm is to be operated in TE11 mode. The minimum operating frequency is, okay, so you see A value and B value is given to you, and operating mode is TE11. So what is minimum operating frequency? That is nothing but the cutoff frequency. So F greater than Fc is going to propagate. So what is the minimum operating frequency? Which is nothing but the Fc itself. So Fc, you need to calculate for which mode? For the TE11 mode. So how do you use that? C by 2 into square root of m by a the whole square. So 1 by a the whole square plus 1 by b the whole square, because n should be 1 in case of TE11 mode. Now coming to the next part, coming to solving this, substituting the value of A is 4 centimeter, B is 3 centimeter. The operating frequency, if you calculate, you get it as 6.25 gigahertz, and that will be the minimum operating frequency, 6.25 gigahertz. Moving on to the next question. For a rectangular waveguide of internal dimensions A cross B, where A greater than B, the cutoff frequency for the TE11 mode is the arithmetic mean of cutoff frequencies for TE10 and TE20 mode. Okay, so the statement says that FC of TE11 mode is mean of FC of TE10 plus FC of TE20 divided by 2. So that's how we take the mean. So that's all. Now, if A, that is the dimension, internal dimension of the waveguide, A is root 5 centimeter, what is the value of B? Okay, so now let's move on to see what is cutoff frequency for each of these. FC of TE10, okay, that is C by 2, if you remember, square root of 1 by A the whole square. So that becomes 1 by A. So that is the cutoff frequency is C by 2A. Now how about TE20 mode? Okay, in case of 20 mode, C by 2 into 2 by A will come. Okay, so 2 and 2 gets cancelled, it becomes C by A. Now take the mean of these two, you will get the cutoff frequency for TE11 mode. TE11 mode, it will be C by 2 into root of 1 by A the whole square plus n by 1 by B the whole square. Okay, so let's take the mean of these two. C by 2A plus C by A the whole divided by 2. So let's take C by A as common. So 1 by 2 plus 1 divided by 2. 3 by 2 by 2. 3C by 4A. And we already know the value of that A. So, and C value is 3 into 10 power 8 divided by 4 into root 5. So this is the FCTE11. Okay, so this you can substitute to here, and A is root 5. So this again becomes C by 2 into root of 1 by 5 plus 1 by B the whole square. Okay, so if you equate this, whatever you get here, if you equate to this, C is a non-quantity, you can find the B. Okay, once you solve it, the answer will be B is equal to 2 centimeters. So this is a numerical type question for which you need to enter the answer as 2.
Coming to the next question. The longitudinal component of magnetic field inside an air-filled rectangular waveguide made of a PEC, that is a perfect electric conductor, is given by the following expression. So this is an expression for HZ. Okay, and the dimensions of the waveguide A and B are given. Mode of propagation inside the waveguide is being asked. Okay, so to find the mode of propagation, always remember we need to look at the expression, the HZ expression. So if you see HZ is not equal to 0, but EZ is 0. So from there itself we get the idea that EZ is 0, it's a TE mode. Okay, TE mode. Now HZ, now if you look at the HZ expression, it's of the form cos of 25 pi x cos of 30.3 pi y, then multiplied by cos of omega t minus beta sl. Okay, so this is the last part. So let us focus on these two parts. So this is of the form m pi x by a, and this is of the form n pi y by b. Now how to solve it? M pi x by a. So you will get a, you know the value of a here. So you can write it as m by a is equal to 25. M is equal to 25 into a value is 0.08 meters. So you will get the answer as 2. So m value is 2. Now similar way, n by b is 30.3. So n will be 30.3 into b value. What is b value? 0.033. Okay. So multiplying this, you will get it as 1. So we know it's already, we know that it is TE mode. What is m and n value? TE21. So this is TE21 mode. Moving on to next question. Air-filled rectangular waveguide of internal dimension A into B has a cutoff frequency of 6 GHz for the dominant TE10 mode. So first data from the question is, in case of TE10 mode, which is the dominant mode, cutoff frequency is 6 GHz. For the same waveguide, the cutoff frequency for TM11 mode, okay, TM11 mode, FC is equal to 15 GHz. Okay. Now, cutoff frequency of the TE01 mode. This is being asked. So, from TE10 mode, so we do not know the value of A and B, but if you look at the expressions for FC is equal to C by 2A in case of TE10. So this can be equated to 6 gigahertz. Okay, 6 into 10 power 9, where C is 3 into 10 power 10 centimeters. Okay, so from this we can write A value. A value is 3 by 12, so 1 by 4, 1 by 4 into 10 it comes, so 2.5 centimeter. Okay, so that is A value, let it be. Now similarly for TM11 mode, we can write the expression as C by 2 into square root of 1 by A the whole square plus 1 by B the whole square is equal to 15 gigahertz, 15 into 10 power 9. Here we already know the value of A, substitute that A as 2.5 centimeter, and you can find the value of B because we already know C. Okay, so from this we can find what is B. So once you find that, for TE01 mode, what is FC? C by 2 into square root of 1 by B. So C by 2B. Okay, once you get the value of B, substitute here, you will get the cutoff frequency for TE01 mode. So while solving, you must be getting B value as 1.09 centimeters, and finally the cutoff frequency you must be getting 13.75 gigahertz. Okay, moving on to the next question. A standard air-filled rectangular waveguide of dimensions A 2.29 centimeter and B 1.02 centimeters are designed for radar application. It is desired that these waveguides operate only in the TE10 mode, with the operating frequency at least 25% above the cutoff frequency of the TE10 mode, but not higher than 95% of the
next higher cutoff frequency. The range of allowable operating frequency is the question. Okay, so we know the value of A 2.29 centimeter and B 1.02 centimeters. Now, the waveguide operating frequency, okay, it should be 25% above the cutoff frequency. So let us say FC for TE10 mode. Okay, so let us find out what is that. That is C by 2A, 3 into 10 power 10 by 2 into 2.29 centimeters. So you will get the answer as 6.56 gigahertz. Okay. Now, 25% above. So this has to. So the waveguide has to operate 25% above this particular cutoff frequency. So that will be 25% above means 1.25 Fc. Okay. So 1.25 into 6.56. So this is something like 8.2 gigahertz. Okay, so if you see, so this has to be above. So the operating frequency has to be at least 25% above the cutoff frequency of TE10, and but not higher than 95% of the next higher cutoff frequency. So after TE10, which mode comes? So after TE10, the next higher mode is TE20 mode. Okay. So TE20 mode, it will be C by 2 into 2 by A. So or we can say C by A. So it is 3 into 10 power 10 divided by A value is 2.29. So we will get it as 13.1 gigahertz. So 95% of the next higher. So zero point 0.9, okay, 0.95 of this FC TE20. Okay, 0.95 into 13.1. That will be 12.45 gigahertz. Okay, so the range of allowable operating frequency, if you see the options, it is very clear that it is between 8.2 and 12.45. So it will be option B. Option B will be the right answer. So the idea here is understand what is the cutoff frequency as TE10. 25% above that cutoff frequency will be the minimum operating frequency, and understand the next higher order mode is TE20. 95% of that one's cutoff frequency will be the maximum operating frequency. So allowable range will be between these two. Moving on to the next question here. The cutoff frequency of TE01 mode of an air-filled rectangular waveguide having inner dimensions A into B is twice that of dominant TE10 mode. So let us write the first statement in a uh, understandable way. So cutoff frequency FC of TE01 mode is 2 times that of FC of TE10 mode. Okay. So this is the first statement. Now moving on. When the waveguide is operated at a frequency which is 25% higher than the cutoff frequency of the dominant mode, so operating frequency is 1.25 into FC, which is basically TE10. Okay. The guide wavelength is lambda g is 4 centimeter, and find out the value of B. Okay. Now FC is FC of TE01. So from this equation we can write C by 2B is equal to 2 times C by 2A. Okay. So 2 and 2 gets cancelled, C and C gets cancelled. We can write from here A is equal to 2B. Okay. Now F operating frequency is 1.25 times FC. So 1.25 FC is 3 into 10 power 8 by 2A. So that will be the operating frequency. Now for this particular operating frequency, the guide wavelength is known to us. So if you know the expression of guide wavelength, lambda g is equal to lambda by square root of 1 minus fc by f the whole square. Okay, fc and f. So fc is the cutoff frequency and f is the operating frequency. So if you substitute the value of these two, this is going to be 4 centimeters. So from lambda g, you can calculate lambda. Okay. Once you know the lambda, you can come back to f. So once you get f, from f, so you calculate, once you calculate f, fc can be calculated. And a and b values can also be calculated from the value of f and fc. So let us make it more clear. Lambda g is equal to lambda by square root of 1 minus fc by f the whole square. So fc by f, so lambda g is 4, lambda by root of 1 minus 1 by 1.25 the whole square. So this is the ratio. So from this, lambda is 2.4 centimeters. So f is c by lambda. 3 into 10 power 8 divided by 2.4 into 10 power minus 2. So you will get the value as 12.5 gigahertz. So this is F. Now FC. FC is 12.5 into 10 power 9 divided by 1.25. that is 10 gigahertz. Okay, now this frequency Fc is, we know that it is equal to C by 2a. So 10 into 10 power 9 is equal to 3 into 10 power 10 by 2a, where a is 3 by 20. Okay, 3 by 2 centimeters. Similarly, b is a by 2, so 0.75 centimeters. So this is the dimensions of the, so basically what is asked is value of b, so value of b is 0.75 centimeters. Thank you.